Good afternoon. I'd like to present an international team featuring a rare combination of both security experts and academics who are here to present the first meaningful real-world attack on MD5. So, please.
Hi, and thank you for having us. I'm Jake Applebaum, and this is Mark Stevens, and this is Alex Sodorov. And today we're going to talk about MD5 and how it should be considered harmful today, and how we've created a rogue CA certificate. And so we're also joined here by David Molnar, and we also have over here on the very far left, Bene, is that, yes? So, and also Arjen on the right. And so Alex and I are the security researchers, and these guys are the academics. So just to, in case, these are the organizations in which we're from. So essentially, we noticed that real certificate authorities actually still issue certificates signed with MD5. And this is something that's quite incredible, since MD5 has been known to be broken since 2004. So there was a theoretical certificate authority attack published in 2007. Can I get a show of hands of people here that saw that or heard about that? Okay, so the people that did that attack are the academics up here. So it seemed like a great idea to collaborate. So what we were able to do while collaborating here was that we were able to, as I said, create a rogue certificate authority, and it allows us to do completely transparent man-in-the-middle attacks on anything that uses SSL. This isn't a specific critique against SSL. This is about digital signatures, and we're using SSL as an example, specifically because of the real-world use. So the way that we did this was with MD5 chosen prefix collisions and a cluster of 200 PlayStation 3s. Funded by the Swiss taxpayers. Thank you for your neutrality. That's very good. So what we're going to talk about in this is essentially split up, as you see right here, and I'm going to now tell you about a live demo. This is our backup demo, because our previous demo had a problem. It worked, so we tried to change it. What can I say? Go Linux. If you can reach .3 on MD5 Collisions Inc., on the wireless network, you can try to man-in-the-middle yourself live for every single site on the internet, if you would like, specifically on port 443. And please don't burn your remote roots on this machine. Thanks. But you can also go to this URL right there and check out the certificate chain. And the certificate chain should be of interest to you. You'll need to set your clock back to August 2004, because we intentionally crippled the certificate. This is not a limitation of our attack, but specifically because we wanted to limit a number of things that could possibly go wrong. But please understand that we set the expiration to 2004. This was not the certificate authority. So we could have easily set it to expire in 2038, for example. So we're going to talk about public key infrastructure. So basically, SSL is used for, well, I don't know, who here doesn't use SSL? Raise your hand. Okay, that's good. All of you use SSL. Excellent. Okay, so the attack tool that I wrote basically works by man-in-the-middling all the connections and simply relaying them and issuing certificates based on what the opposite side of the connection has in its certificates. So POP3 and IMAP, as well as IRC SSL, fell over instantly. It was very easy to write like basically no code to do this, and it just works perfectly out of the box. And using this, it's been really interesting because we've also found hilarious bugs, like IRSSI actually doesn't care if the certificate chain is expired. Whoops. Yeah, so it's maybe not the world's greatest thing. SSL is, of course, used all over the world for lots of other things other than these examples. And basically, if you have the trust root in your certificate store that we have compromised here, you're perhaps in trouble. And if you have MD5 certificate authorities, those that issue certificates with MD5, that's maybe not the world's greatest thing. So essentially, it allows for everything that is your worst nightmare. And there's a lot of talk about what could possibly happen if we hadn't had SSL with the big Kaminsky DNS bug. So this combined with that is almost like unimaginably bad, I suppose. Firefox 3 is really interesting. It has 135 trusted certificate authority certs. So like Turk Telecom, just for example, I think has like 3 or something like this. If you look at it, you'll see that the certificates aren't constrained in any way. So any of those certificate authorities can issue for anybody. And that's not so great. And the CA supposedly has this responsibility to make sure that when you request a certificate, you are who you say you are. But this doesn't always work out well. There's a high-profile incident where Microsoft.com certificates were issued by VeriSign to like some unknown party. And this can be a really big problem. But that's just one certificate. So just having a single certificate is not necessarily the end of the world, except for a specific targeted attack, maybe. But as far as having the ability to have a certificate authority below that, it means that you can issue them for anything, and you only need to pull the attack off once. That's the real key thing. So they're supposedly also supposed to be responsible for revocation, but if you remember the Debian OpenSSL bug, you probably know that that didn't work out very well. So here's basically the idea here for those watching at home. Essentially, we've got the root CAs, and then some of them delegate out trust. Just a couple days ago, there was a Startcom blog post that talked about how a guy was able to get a Mozilla.com certificate, and the way that he did it was by simply saying he was Mozilla.com, and some reseller that didn't do any sort of like validation of his credentials simply issued him Mozilla.com, totally valid. Of course, it wasn't a CA, but that's not bad if you wanted to specifically attack Mozilla. And so this complicates matters as far as checking certificates. So essentially, if anybody here has ever generated a certificate signing request, you know that basically the steps are that you need to have your domain name, you've got like the information you fill out that the certificate authority requires of you, and it has the public key. The CA basically will take this certificate signing request, it parses it and it says, okay, this is foxnews.com. I'm going to check that out somehow. Usually it looks by sending an email to hostmaster at the domain or something like this, and you have to click a little link and maybe solve a CAPTCHA or something like that. And if you pass their checks, then they give you a certificate. And then you, as the user, will of course take that legitimately and put your private key and the certificate in place. And in theory, this is a great idea. And this is where we'd like to introduce our secret weapon, Mark.
Hi, yes, now I'm going to sketch a little bit about MD5 and the attacks that have been against it. And, well, as you know, MD5 is a hash function and was originally designed in 1991. And it's basically an iterative design using a compression function. So it picks a message and it splits up in blocks, and then it will just process it sequentially, all those blocks, until finally you get the hash value. And so basically what we're working with are collisions. So that means that there are different messages that have the same MD5 hash. So the first MD5 collision attack was presented in 2004 by a Chinese team of researchers. And they were all able to create collisions, 2 messages of only 128 collision bytes, and that had the same hash. Currently, this attack can actually be done within 1 second just on a regular PC. This collision attack is quite limited because the only difference that you have between the colliding messages are those 128 collision bytes, and that can be anywhere in the messages. The messages themselves can be very large, but the only difference between them can be in 128 consecutive bytes. So what can you do with this kind of collision attacks? Well, for a collision attack, you can do this attack, generate specific collision blocks somewhere in a file, and you can use a document format. For instance, there was an example with the PostScript files, and PostScript supports like an if-then-else statement, and it just compared which collision block was present, then it showed one contents, and in the other case it showed the other contents. So, and that's the case for this attack. If you use an if-then-else construction, both payloads must be present in both files, and that's quite a restriction. So there were these colliding PostScript files that were done in this way, but other documents are also, it's also possible to do this attack for like Word documents and PDF files. Also colliding executables examples have been shown, and well, of course, both both payloads have to be in there, but the two different messages have different execution flows. Now in 2007, our chosen prefix collision attack came up, and it's a much stronger collision attack. And because in the earlier attack, only 128 bytes can differ. With our chosen prefix collision, basically almost the entire message can be different. So like the picture shows, you can just pick the first part of the message any way you like. For both kinds, you can choose them both freely. And then we just add 716 collision bytes, and there it is. There's an MD5 collision. And whatever you append after it, if they're equal, it remains an MD5 collision. And such a chosen prefix collision currently only takes 1 day on a single PlayStation 3 and a PC. So what can you do with this chosen prefix collisions? Well, this is a second generation attack scenarios order. You don't need if-then-else statements necessary in these document formats. So that means that each file just contains the single payload instead of both. Well, with regard to colliding executables, this means that the malicious payload will not be present in the harmless executable. So it will not be obvious that there is any harm in this harmless executable. And also, this also applies to documents where these collision blocks, to make them collide, can just be put inside raw image data that's in an image that won't even show in the document. So how we're going to use these chosen prefix collisions or MD5 collisions to generate colliding certificates? Well, if certificates consist of two parts, the to-be-signed part and the signature itself. So if the to-be-signed parts collide, then the signatures will be identical for both certificates. So how can you use it? Well, you generate a pair of colliding certificates with colliding to-be-signed parts. You get the legitimate certificate signed, and now you can copy the signature into the rogue certificate. So in previous work, the first collision attack, the 2004 collision attack, colliding certificates were made, but yeah, those 128 different bytes were only in the RSA public key. So the identities in both certificates were exactly the same. So this wasn't really impressive. Now in 2006, with our chosen prefix collisions, we could just take whatever identities we wanted and use the RSA public key to make them collide. And then we had colliding certificates with different identity. And these chosen prefix collisions well, have been known since 2007. Oh. So this is kind of the attack you would have with a 2004 collision, the chosen prefix collision attack from 2006. So you just have two certificates. The red parts are the chosen prefix, and that will contain the different identities, and on the left side you will have a serial number and a validity period, and it just falls off the screen, that are set by the CA. But on the right hand side we have a serial number, validity period, that we can pick ourselves. Now the computation will be put into the RSA key part, and that will just look random, and then the rest will be exactly the same. Both the 509 extensions and, most importantly, the signatures will be the same. So, Alex? Yeah.
All right. So now we're up to 2008, and in 2008, David Molnar, Jake, and I started looking into SSL and thinking about ways you can break it. We came across the paper that the other members of our team had published, and at that point we did not know them. But we realized that we would need these kinds of techniques in order to execute this attack. So through David Molnar, we got in touch with the other guys, and they graciously agreed to collaborate with us on doing this attack. The problem that they had in 2006 was that doing this attack against a real certificate authority was